Hello everyone. We're discussing Gauss, and in Gauss we need to find the calculating electric field of an infinite sheet of charge. That infinite sheet of charge, I gave you enough hint to solve that question. Is there anyone who has got the answer in this spot? The question which I gave you in the last class, answer is sigma upon 2 epsilon 0. If anyone has done this and got the same answer, then write down yes in the comment box. Rest, look here. This is the infinite sheet which is uniformly charged. And charge density is, surface charge density is sigma coulombs per meter square. I told you that for this type of surface, for this type of charge, we will draw a Gaussian surface which is in the form of a cylinder. This is the cylindrical Gaussian surface. But instead of drawing this figure, it's better if we draw the whole thing in this form. This will be called side view. What is a side view? In side view, this whole thing will look like this. This is the infinite charge layer. This is the front view. And instead of front view, we are interested in the side view, like this. That's side view. Now, for this side view, this Gaussian surface is in this form. This is your Gaussian surface. In the form of a cylinder. These two are flat portions and this is the curved portion. The whole thing is a cylindrical Gaussian surface placed like this. That's your Gaussian surface. As flat surfaces, at the same time it has what? Curved surfaces. So, for an infinite sheet, I told you that electric field at every point of the flat surface, it will be E. 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 Why? I gave you the logic for this in the previous class. What was the logic? That if this is the infinite sheet, then every point in front of this board, every point is an identical point. All they are what? Same. The reason you can go through the lecture which I gave you in the previous class. Now, this is your electric field and this is the area vector. For this flat portion, this is your area vector A. If you are at this place, your area vector is in this direction. That's your area vector. Area vector is always what? Away from the closed surfaces. It is always along the outward normal. If you are somewhere here on the curved surface, then for curved surface your area vector is this, and electric field at any point is this. The angle is what? 90. These are the three portions. For curved surface, angle between electric field and area vector is 90. For flat surface, the angle between electric field and area vector is what? 0. Now, Gauss says total flux, which is E dot dA, should be charge inside divided by epsilon 0. That is from Gauss. This whole thing is your phi total. Capital T for total. Phi total. Electric flux total associated with the closed surface. This phi total, we break it in two parts for a cylindrical surface, which is phi for the curved portion plus phi for the flat portion. Curved and flat portions. For curved portion, you can see flux is what? 0. Angle is what? 90. For flat portions, E and A, they are parallel, and therefore you will write E into A, that's also at cos 0, plus E A cos 0. E A cos 0, E A cos 0 for these two flat portions. This is through the curved surface, and the whole thing is charge inside. What is charge inside? Now let's look at that. If you have a cylinder, then when you place it like this, then this is the area of the infinite sheet which will be inside the cylindrical Gaussian surface. Nothing special. If this board is your infinite sheet and this is the cylinder, this flat area is A. If I place a cylinder like this, I hope you can see, when I place it like this, then the portion of the board which it occupies is same as A, and therefore this area is also what? A. So what is charge present on the infinite sheet? Sigma coulombs per meter square. That is charge per unit area. On unit area you have this much charge. On area A, charge will be sigma A per unit area sigma on this area A, which lies inside the cylinder, charge will be sigma A divided by epsilon 0. This is your pi total. Left side is what? 2 times EA plus EA, and the right side is sigma A upon epsilon 0. A and A cancelled, and your electric field E is coming sigma divided by 2 epsilon. Sigma divided by 2 epsilon 0. Put on this and then we'll write few points. Yes, we can take cuboid or a cube also. Now get this information. Suppose this distance was R. That means we were interested in finding electric field of an infinite sheet at a distance of R from it. But the final answer, there is no term of R. There is no term of R, then it means what? Simple logic which we used in the last class was saying that if this is the board and the board is of infinite size, infinity, 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 then you consider this point at some distance, you consider another point at the same distance, you consider third point at the same distance, They all are what? Same. This is coming from the logic because all these points they are just in front of the center of the board. Not this board, but a white board which is of infinite size. Center means everywhere you move, your distance will be what? Same. It is of infinite size and therefore that argument holds. So, this was the plain logic which we found that at same distance, your electric field should be uniform. But using Gauss, we also found that for an infinite plate, electric field at this position, at this position, at this position. That is, electric field at this position, at this position, at this position. Even though I am moving away from the infinite sheet, but electric field is still what? Same. And therefore, write down with this that this is an example of uniform electric field. Write down uniform electric field and then write down the statement. Do mention this R. Write down the statement. Electric fields produced by a uniformly charged infinite sheet does not depend upon R. That is, it is uniform everywhere. It is uniform everywhere. When I say uniform everywhere, that means on one side it is what? Uniform. If you come to this side, again magnitude is this, but there is a change in the direction. So the entire region electric field is not uniform. On one side of the infinite sheet, electric field is what? Uniform. And therefore, if they ask you to draw, they can ask you a question like this: draw electric field lines for an infinite sheet, then you can draw a separate figure and then you should draw electric field lines like this. This is the charge distribution. For this infinite charge distribution, that's how you will draw your electric field lines. That's how you should show these electric field lines. Look at the spacing. They should be of uniform spacing. They all are pointing in the same direction. They have uniform spacing and are pointing in the same direction. One more question you can expect in any examination. Draw electric field lines. Write down the question and then with that question, go down this setup. Draw electric field lines draw electric field lines for an infinite sheet No, you cannot draw a vertical cylindrical Gaussian surface. If somebody draws a vertical cylindrical Gaussian surface like this, if you draw something like this, I hope you can see it, then every point of this curved surface is not at the same distance. Try to visualize in this form. Again, this is the board. If you can see the cylinder, you're supposed to hold it like this. If you are holding, the question is that if you hold it vertically instead of horizontally. If somebody holds it like this, then these points, their distance is maximum. But as you move along the surface, ultimately you will reach near the infinite charge itself, and therefore you cannot write electric flux in terms of E into A. We cannot write it like this. Suppose somebody had told us that electric field is uniform, then we could have. But since we do not have this information beforehand, we have to take a cylinder like this. I hope you understand what I am saying. I hope this figure will be more clear. Look here. You're asking that instead of holding it in this form, one must hold it like this. If somebody holds it like this, then look here. This is the view. You can see the board and the cylinder both. In this case, different points of the cylinder, they are at different distances. And therefore electric field is not uniform. The other question which was asked is that what if we take cuboid, cuboid. There is no issue if we place a cuboid like this. If you place a cuboid like this, then again, for this cuboid, this face is in this form. This is the face. All other faces, 1, 2, 3, 4, these 4 faces, angle between area vector and electric field is 90, and therefore flux will be what? 0. Instead of saying curved surface, you will say the side faces like this. Only this face and this face, electric flux will be present through these spaces only. The aim is to produce a surface for which we can easily calculate electric flux E into A. You can have any type of Gaussian surface. Ultimately, that will be Q inside upon epsilon 0. But the problem is, it won't be possible for us to measure electric field. And therefore, we are drawing a Gaussian surface which can easily find us electric field at some distance r. Now note down electric field due to an infinite electric field due to an infinite uniformly charged conducting plate. Electric field due to an infinite uniformly charged conducting plate. In this example, we had an infinite sheet, but now we need an infinite conducting plate. Infinite conducting plate. Now what is this is uniformly charged. Uniformly charged infinite conducting plate. What is the difference between an infinite sheet and an infinite plate which is conducting? Write down a statement. You will understand the statement later on properly once we develop concept of electric potential. But still, write down the statement. Inside a conductor, electric field inside a conductor, electric field is always zero at equilibrium. At equilibrium. What is a plate? Conducting plate is this. This is your plate. This is a plate which has two faces. A plate has some thickness and there are two faces. Two faces. Infinite sheet also has two faces, but it is just a single layer of charge. Whereas if you have a plate like this, then its side view will look like this. Proper side view will look like this. This is the plate side view, and you have charges on the surface. The charged plate, our aim is to find electric field at a distance of r. This is the aim. This is the side view. Now, once I say that electric field inside a conductor, it's not about conducting infinite plate. Remember, it's a general statement. A conductor of any shape and size at equilibrium. At equilibrium means when you switch on and fan starts rotating, or your AC is working, or the light is on, in that condition, we have the copper wire, and in that copper wire, electric field is present, and because of that electric field, electrons are moving. This is something which we will study in electric circuit, which you know also is called electric current. But that is not an equilibrium or a steady state condition. Electrons are continuously moving because they are being forced. But if you have a conductor and you give it some charge, aluminum, iron, copper, any volume, you give it some charge, then this charge distribution will take place such that at any point inside, electric field is what? Zero. Why should it be zero? We'll see that. There are two ways to understand that, and we'll understand with the help of both those things. But right now, the only thing you need to know is, if you have a conductor, inside there will be no electric field. And if there is no electric field inside, then Gauss says flux will be zero, and therefore there can be no charge inside. So, inside a conductor, in equilibrium, there can be no charge present. You add this line also with the statement where you have written that inside a conductor there can be no electric field. Continue that statement, which also means that there can be no charge inside a conductor there can be no charge inside a conductor at equilibrium. Now for us, what does it mean? For us, it means we have this side view and all the charge is present on this space and on this space. These two faces. What is the difference between an infinite sheet of charge and an infinite plate. In infinite sheet of charge, you have a single layer, whereas in infinite plate of charge, you have two layers, like this. I hope you understand the meaning of infinite plate. Now, once I say this, if they ask you this question in board or school, you write all these points. It's a conductor, there can be no electric field inside, there can be no charge inside. Draw this. Once you have drawn this, next thing is very easy. This is your cylindrical Gaussian surface. These are the flat portions. For these flat portions, your electric field and your area vector are in the same direction, exactly like this. For the curved portion, electric field and area vector, they are making an angle of 90. Charge is sigma coulombs per meter square. When you write phi total, again same thing, Gauss E dot dA for closed loop is equal to Q inside divided by epsilon 0. You will write this formal statement, and then again same thing, phi total is what? Phi curve plus phi flat. Curved portion and what? Flat portion. Curved portion, your flux is what? 0. Through the flat portion, flux is what? EA cos 0 plus EA cos 0. Plain and simple repetition. The same thing. There are two surfaces, flat, EA cos 0, EA cos 0. Curved surface, there is no flux, angle is 90. What is charge inside? When you had a single sheet, there was only one charge distribution, but now there are two charge layers inside. This sheet and this sheet, and therefore charge inside is what? Sigma A into 2. There are two layers divided by epsilon 0. This is 2EA, A and A cancelled, and your electric field is coming sigma divided by epsilon 0. The result which we got for previous article, double of that, is your electric field, and this electric field is also what? Uniform. If you understand this much, then note down this and write down yes in the comment box. If you are confused, write down your confusion. Now we discuss that. Now they can also ask the same profile in this form. First, they will ask you that find out electric field of an infinite sheet with the help of Gauss, which we did in this part. And then they can ask you, with the help of that result, obtain electric field produced by an infinite conducting plate. If question is asked in this form, in fact, write down this question. This was what? This was electric field of an infinite conducting plate directly using Gauss. Directly using Gauss. Now write down electric field of an infinite plate. Electric field of an infinite plate with the help of electric field of an infinite sheet. So here, this is your infinite sheet of charge. And your electric field is given by sigma upon 2 epsilon 0, and this electric field is independent of R. It has nothing to do with R. This is your infinite sheet. Now, for infinite conducting plate, this is your infinite conducting plate. Just so that we can see it clearly, I have increased the thickness. And these are the two charge layers. Remember, this end is at infinity. This end is at infinity. Some of you get confused and they start thinking that some charge will be present over here. But the thing is that this position is at infinity. And where is infinity? If somebody is interested, go find infinity and then come and tell me. So remember, these two ends, they're just shown like this. They are at infinity. Now, if you're not interested in the Gaussian part, this is the second method for infinite plate. For this infinite plate, we are using this argument. The electric field of an infinite sheet is sigma upon 2 epsilon 0 and is independent of R. Which means over here, somewhere here, electric field due to this layer is what? Sigma upon 2 epsilon 0. At the same time, electric field at this layer due to these at this position due to the second layer is also what? Sigma upon 2 epsilon 0. Now, our intuition says that this charge is closer and therefore electric field should be more powerful. But we have found that electric field of an infinite sheet is independent of R. And therefore it doesn't matter you are at this distance or you are at this distance. In both cases, these infinite sheets are producing same strength, giving you what? A total electric field. So at this point, your total electric field is coming what? Sigma upon epsilon 0. Sigma upon 2 plus sigma upon 2 is coming what? Sigma upon epsilon 0. Now, look at the second part and then note down everything. Or do one thing. Note down this, and think about the question I'm going to ask you. Think about a solution to that. With the help of this, the electric field of an infinite sheet, can you see that with the help of the result of infinite sheet, we can prove that inside a conducting plate electric field should be 0. With the help of this result, if you can see that inside electric field is 0, if you can see it, the moment you see it, write down yes in the comment box. What do you mean by this statement that, sir, shouldn't there be two electric fields associated with one curved surface? What are you basically asking? Yes? I'm not, you're talking about this figure. Which one? This. फर्स्ट मेथड में इसमें क्या है फिर से पूछो क्या पूछ जो एक साइड चार्ज है वो भी एक इलेक्ट्रिक फील्ड लगाएगा और जो दूसरा साइड चार्ज है वो भी इलेक्ट्रिक फील्ड लगाएगा और दोनों के बीच में कुछ थोड़ा डिस्टेंस है तो दोनों की इलेक्ट्रिक फील्ड को And we have no idea what that electric field is. If you are using Gauss, we have no idea what is the electric field produced by this and this is. But somebody told us that that electric field is E. This electric field E is due to this charge as well as this charge. When I say this charge, remember all the charge over this side, all the charge over this side. All these charges, their electric field at this position is what? E. And what we know from the logic is every point of this flat surface is identical, and therefore everywhere you go, electric field will be E. Whose electric field is this? We do not say that this electric field is of this charge or is of this charge. What is the statement of Gauss? When you write Gauss, what is the statement of Gauss? Whose E is this? This E is electric field of any charge which is present inside or outside. So, this electric field automatically is of each and every charge present on this infinite conducting plate. You do not differentiate like this or this. Gauss says, whose E is this? Of any charge. We differentiate between this and this when we have to have the right side. The right side is what? Q inside. So Q inside you will see this charge as well as this charge. So what I was asking is that do you guys see that electric field inside the conductor is zero if we know the result of electric field of an infinite sheet charge? Nobody has responded so far. Can you figure out this? That using this information, we can prove anywhere inside electric field should be zero. If you can visualize this part, then write down yes in the comment box. Look, there are two infinite layers. This is the conducting portion. This is the region where you are inside the plate, remember. You are interested in this portion. Now, this infinite layer, its electric field over here is in this direction. Is sigma upon 2 epsilon 0. Forget about this. Electric field of an infinite layer is what? Sigma upon 2 epsilon 0. And what is the direction? Direction is what? Away from the positive charge. Away from the positive charge. If you are here, then this is the direction of E. Away from the positive charge. So for this, over here, we calculated electric field in this region. But now I need electric field at this place. Now look at this second layer. Let's call it first layer and call it second layer. Then remove the confusion. This electric field is of first. This arrow is for the conducting region. This second charge, its electric field will be what? E2. This second infinite sheet, its electric field is what? E2. And what is E2? E2 is sigma upon 2 epsilon 0. It is independent of R. So it doesn't matter what this distance is or what this distance is. This positive charge, its electric field is E2. This positive charge, its electric field is E1. Anywhere inside you go, E1 and E2 are of same magnitude and they point in opposite directions. And therefore, they will cancel out each other, giving us E inside the conducting region. E inside the conducting region as what? 0. Now, those of you who did not write yes before, if they understand it now, then write down yes in the comment box. If you are confused, I have seen before that people, they are confused in these directions and all. There is no issue. If you think that you have something to ask, you can always write your doubt in the comment box, or you can switch on your mic and ask me anything. Put on this much. Also write down the whole thing in the form of a statement. Anywhere inside the conducting region, electric fields produced by side charges are equal in magnitude and opposite in the direction. Therefore, they cancel each other. and total field becomes 0. And total field becomes 0. Now, just so that you understand this Gauss and all, we'll use a third method for an infinite plate. Third method is based on Gauss. And I will give you some time. I will draw the figure, and then it's your responsibility to produce the same answer. This is your infinite conducting plate. This is the third method using Gauss again. The Gaussian surface is this. This is the Gaussian surface. In the first method, your Gaussian surface was this. This was the Gaussian surface in the first method. But this time, this is the Gaussian surface. Draw this, and you've got 1 minute's time. Find electric field over here, and everything is given in that statement where I told you in the very first method. First method says what? Inside a conductor, there can be no electric field, there can be no charge. If you are using third method, then you can always write that statement. Inside a conductor at equilibrium, there can be no electric field, there can be no charge. Draw this, and the moment you get the answer, which is sigma upon epsilon 0, write down yours in the comment box. It's a very easy question. Give it try. Only 2-3 have responded so far. This is the direction of electric field. This is the direction of area vector. This is the direction of area vector. This is your electric field, which is 0. This flat surface which lies inside the conductor has no electric field. Curved portion, electric field is present. Angle with area vector is 90. This is the setup. For this setup, once you write phi total, this is phi curve plus phi left side flat surface plus phi flux through right side flat surface. This is flux, which is what? I've broken the whole thing in 3 parts. Curved, left side flat and right side flat. Your phi total is coming 0. What is the reason behind this 0? Angle is 90. This is 0 because of 90 degrees. This is for your understanding. This 0 is coming because of the 90. Left side flat, again flux is 0. This is 0 because electric field itself is 0. Where? In this region. And for the right side, definitely you have the flux as what? E into A. Cos 0, which is 1. What is charge inside? For a Gaussian surface like this, you had 2 layers of charge inside. But this time only one layer is present. Only this layer is present. Single layer. And therefore charge inside is what? Sigma into A divided by epsilon 0. A and A cancelled and your electric field is coming sigma divided by epsilon 0. Same answer. Mention everything in this form. These are for your understanding. This is 0 curved surface because that curved surface angle between electric field and area vector is what? 90. In school and board, if they ask you, then you can write the whole logic. Electric flux to the curved surface is 0 because angle is 90. Electric flux from the flat surface, left side flat surface is 0 because this surface lies inside the conducting plate where there is no electric field. Note down this. I've given you 3 methods. In school, board examinations, you can use this or this if they ask you to find electric field with the help of Gauss. If they ask you to find electric field with the help of infinite sheet, you have this method. With the help of these 3, you can easily, I hope you can easily understand the way concept of Gauss is developed. Now, just look at this logic. Why do we say that electric? Why do we say that charge inside a conductor is zero? We'll use a plain and simple logic, and the detailed logic will develop later once we have the concept of potential and all. Right now, we are using simple logic. Suppose you have a conductor. Conductor means charge can move. So, suppose you have a big piece of copper, solid piece of copper, and somehow you gave it charge in its volume, positive charge. So, you have situation like this. We'll take help from a spherical piece of copper, because sphere is something which we will develop later on. This is a spherical piece, and somebody gave charge inside the volume, and developing a intuitional argument which everybody can understand without using much of maths. So this is a conductor, remember, I take copper, and it has been given some charge. What is copper? Copper is a conductor. What do you mean by conductor? Conductor means charge can flow, charge can move. Now, all these charges, they are repelling each other. Positive charge. They are repelling each other. When things repel and they are allowed to move, conductor, conducting, things can move. They are repelling each other and they can move, then they will go to that place where separation between the charges is maximum. So when things they repel, these charges when they repel, they will ultimately move to the outer boundary of this shape. It can be any shape. It can be a spherical shape, it can be a cubical shape, it can be any irregular shape, doesn't matter as long as it is what conductor. If you give it some charge, that charge will repel each other, and ultimately because of that repulsion, whole charge will rearrange itself over the surface. Once charge is on the surface, there is no charge inside. And therefore we say that inside the conductor there is no charge. If there is no charge, there will be no electric field. Do you understand this plain and simple logic, which is simply based on what? 9th and 10th class logic, repulsion. If you understand this logic, simple logic, then write down yes in the comment box. Let me see how many of you have understood it. It's coming from the intuition part. And remember, there is no harm, again and again I am telling you, there is no harm if you say no. If you do not understand it, you cannot feel it, you can always write no. Write down the statement. If some charge is given inside a conductor, if some charge is given inside a conductor, then due to electrostatic repulsion, between individual charges, all the charge rearranges itself over the surface of the conductor. Over the surface of the conductor. And therefore, at equilibrium, there can be no charge inside a conductor. There can be no charge inside a conductor, and therefore, according to Gauss, there can be no electric field inside the conductor. Therefore, according to Gauss, there can be no electric field inside the conductor. We are handling things all the way around. We have proved first there can be no charge. Once you say there is no charge, then what is Gauss? E dot dA is charge inside. Charge inside is 0. There is no flux, and we are saying there is no electric field. So this thing just mention like this. This is the initial format. Somebody gave it charge like this. Then within a fraction of second, the whole charge will rearrange itself over the surface. This becomes this finally. This is the final setup. You gave it some charge. Within a fraction of second, charge is now over here. Why? Because it is a conductor. If you want to keep charge inside, you must choose an insulator. We'll see that part later. Put on this, and then you can leave. Thank you very much.